Okay, welcome back, everyone. And we have, oh, excellent, Evan, keeping with the themes. Very good. Evan Schneider, Dr. Evan Schneider, is going to talk to us about mass loading. I'm particularly excited about this one, and she's doing so as a cat. So please welcome Evan Schneider.
I am so sorry. Sorry about that. Don't know how that happened. Okay, you can see me now? Great. Right, I was tasked with telling you about mass loading in galactic outflows, and I'm trying to keep this sort of tutorial-y, and less talk-y, but we'll see how that turns out. Yeah, I didn't need an assistant to turn it off. Okay, so I made myself a little outline to try to keep us all on track here. So I'll first try to present some context. Even in a tutorial, I can't give a talk without giving some context. And then some basic definitions for mass loading. I think a lot of the confusion around this particular topic comes from the fact that this is not always defined the same way. Then I'll spend a little bit of time talking about how we measure mass loading with an emphasis on simulations, since that's what I'm most familiar with. I'll talk a little bit about measurement and observations, but I'm sure we're going to hear a lot more about that from Tim tomorrow, so I won't spend too much time there. And then I'll end, if we have time, with a little bit on additional loading parameters that I think can also be very helpful in trying to understand this sort of broad topic. Okay, so for some context, this slide is all you need. The point being, right, we've seen this several times at this point, but what we're interested in is, how do galaxies remove their gas? And we're interested in that because we think that the process of removing gas from galaxies, or at the very least removing gas from halos, is an important one in galaxy formation, and perhaps is responsible for setting many of the properties of galaxies that we see today. And so, one of the ways that we try to parameterize this is by measuring mass outflow rates, and associated with that, this parameter that we call mass loading. Okay, so what is mass loading? Going from, I guess, terminology that you might be more familiar with to terminology that perhaps you're less familiar with. Most commonly in our field, I think mass loading is defined as just, it's a way to measure how much mass is leaving a galaxy relative to its star formation rate. That's the most common definition I think that you'll see. But in the wind community, it is also very commonly defined as a way to measure how much additional mass has been added to a wind. Typically, we're talking about the low density phase of a wind relative to what you might expect to see from, say, the byproducts of stellar evolution, just supernova ejecta and stellar winds. When I was starting this presentation, I decided to go back and see if I could figure out when this term mass loading entered the galaxy wind literature, and actually I found that it was really prevalent in the planetary science and plasma physics community. So it starts showing up in ABS, not in the context of galactic winds at all, but to describe how, for example, a comet that's outgassing might be adding mass to the to the solar wind plasma, and how that might change its properties. So suffice it to say that what mass loading is depends very much on the context in which you hear the term. So that's something to keep in mind. I'll talk just quickly about those first two scenarios, because this is something that confused me a lot as a graduate student when I was starting to read these papers. So scenario one, I said, is I think the most common, mass loading as a way to measure how much mass is leaving a galaxy relative to its star formation rate. So this is the typical formula you'll see. Can you all see my cursor? Yeah, great. Right, so m dot wind, just meaning the mass outflow rate in the wind that you're measuring, is equal to some factor, here I'm calling it eta, times the m dot star formation rate. So just the masses formed in stars as a function of time. And this parameter eta is what we call the mass loading factor. So often, we will present values for eta rather than just say outflow rates. And it's worth noting that eta in this context can have any value, right? So if you have, a high star formation rate and not very much mass in the wind, you can have a very small value for eta. In a sense, you could even have a negative value for eta, right? If you have an inflow. And so there's nothing particularly physically meaningful in this parameter eta. It just relates these two quantities. Okay, scenario 2 that I said, comes up a lot in the wind community is how much additional mass has been added to a wind relative to these byproducts of stellar evolution. I attribute this to the fact that this is actually the way the mass loading factor is defined in the famous Chevalier and Clegg wind paper, right? So there, the idea was you're measuring m dot wind, say in the hot plasma, the very low density wind phase, which, for the record, is the one that we are the most certain is actually a wind. It has high velocities, supersonic, will actually escape. And so there, the mass loading factor, which I'm going to call beta for this presentation, just to clarify between the two, is a factor that scales between the mass that you see in that wind, say the hot plasma, and the mass injection rate from these stellar processes. So commonly supernova, but you could also include stellar winds, etc. And so something to note, right, is that there actually beta now has a sort of a more physical meaning. For example, it's typically greater than 1. You can only add mass into this phase. So that would reflect, for example, entraining additional ISM material into the hot wind. But it's also worth noting that, in order to measure beta, you have to make an assumption about the right side of this equation, right? So you're making an assumption about the mass injection rate into the wind from these underlying stellar processes. So I think, what I want to highlight here, right, is that it's important to actually think about what you are trying to get out when you are measuring a mass loading factor, because that may determine what kind of mass loading factor you are interested in. Okay, so this is a tutorial, so I decided to give a quick example to kind of highlight the difference between these two. Actually, I think near this will answer your question. So here's an example that just kind of shows you the difference between, say, beta and eta in these two definitions. Let's say you have a Starburst 99 model. It gives a constant rate of mass loss or mass injection, however you prefer to think of it, after 20 million years. And that rate scales with the star formation rate with this scaling. So m dot star here, you can just think of this as supernova plus stellar winds plus whatever, goes as approximately 0.25 times the star formation rate in solar masses per year. Okay, so you can imagine here, if you this is what you would get if you ran like a cluster model. You can put whatever mass you want for the cluster in here. This will give you the mass injection rate from that cluster. Now let's say you have, some region with a star formation rate you think you've measured, say 5 solar masses per year in the nuclear region of M82, and you, measure or fit for a value of beta in the hot plasma, and you get 2. Okay, then how would you convert that to eta in this context? This is not a complicated problem. I just, again, wanted to highlight that these are 2 different measurements and they have 2 different values. Right, so if we know beta is 2, that's essentially just saying that the mass that we measure in the hot plasma is twice what we would expect given the, star formation rate and just the ejecta from supernova and stellar winds. So we get a total mass outflow rate in that case of 2.5 solar masses per year, which then, if you convert it to our more traditional definition eta here, you would get 0.5. Right, so in this case, the scaling between beta and eta is just given by this factor of 0.25 in front of the star formation rate. Great. And in this case, also note, right, the physics comes in here. It's the Starburst 99 model that's giving the relationship between beta and eta in this case. Okay, just a warning. We have not settled on these symbols at all in the literature, so we will often use the symbol beta when we actually mean what I just called eta. So just watch out, right? Just make sure when you're reading a paper, you've read the definition of the mass loading factor before you make assumptions. You know, a factor of 4 might not sound like much, but you know, if you start to rescale that, you could easily be off by an order of magnitude if you've misunderstood what was actually being defined. Okay, so to summarize, what is mass loading? Mass loading is just a scaling between some measured m dot and something else, also in units of mass per time. And I want to say, like, I actually really like mass loading as a concept. I think when you normalize it thoughtfully, for example, as in the case of the beta example, it can give you some actual physical insight into, you know, what is the physical phenomena that's leading to this mass loading. But as Dylan pointed out rightfully in his keynote yesterday, if you normalize it carelessly or you're not really thinking about what it means, then it can lead you to some very confusing conclusions about the driving physics. So, right, as Dylan pointed out, if you at late times are looking at winds that are primarily driven by supernova 1A, but you're scaling your mass loading factor by the star formation rate, you know, this could lead you to some confusing conclusions. So, worth again pointing out, just when you're using mass loading, it's useful to think about what it is that you're trying to understand. Okay, so now on to how we actually measure mass loading in simulations first. So in principle, this is very straightforward, right? This is why we like simulations. You can measure whatever you want generally. So in this case, right, all we want to do is measure the flux that's in the wind or the outflow. I'm kind of using those interchangeably here. In practice, of course, there are a lot of choices left to be made. In particular, right, you might have to decide whether you're going to measure in a plane parallel sense, right, just as a function of height, for example, from a disk, or radial flux outward from the galaxy. Once you've made that decision, you have to decide where to measure, at what height or radius are you going to measure this flux. You have to also decide if you're going to measure the instantaneous rate, right, or the time averaged values. Yeah, frustum, exactly. Maybe a frustum is the right shape for you. So the instantaneous or time averaged I'll touch on a little bit again later, but you know, this is a really important one because I think often the time averaged value gives you more insight into the physics, but the instantaneous value is what observations measure, right? So again, worth thinking about when you're going to compare. And of course, you have to decide, you know, what phase are you going to measure? In simulations, in principle, you can measure the total mass outflow rate in all phases, but if you want to compare to observations, that may not be the right thing to measure. I'll just run through a few examples. I'm not going to touch on cosmological simulations because Dylan basically did that yesterday. But, you know, so starting kind of from bigger and going in, here's an example from the FIRE collaboration. This was from a paper in 2015, just showing you how, for example, a Zoom simulation might measure the mass loading factor. So I would say, on average, cosmological and Zoom simulations are usually measuring radial outflow rates in radial shells. So in this case, say you have SPH particles. This is, again, pretty straightforward. You're just going to sum the outflow rate in the spherical shell. So here this is giving you, you know, m dot is just the sum of this first term, v dot, you know, r over r is just the radial velocity times the mass of the SPH particles. Sum all those up in some, you know, in some radial shell, divide by the width of the shell. This gives you an m dot in the shell. It's worth noting, right, this is a plot then on the right of the outflow rate measured this way at 1/4 of the virial radius, that's the red dashed line, and at the virial radius, that's the, you know, the less dashed line. These values, you know, can be very high, and if you are going to measure an instantaneous mass loading rate from the simulation, here the black line is the star formation rate, actually scaled up by a factor of 10, you can get huge numbers. And particularly in the cosmological context, this is very likely to happen because we think outflows, right, are actually one of the processes that's responsible for decreasing star formation. So if you're looking at an outflow that was ejected by a previous epoch of star formation, then you're likely to see a really large value of eta. Okay. So often, actually, in simulations, we average, and averaging, you know, m dot over some period of time. Here from this fire simulation, they averaged from redshift 2 to redshift 0.5, averaged the star formation rate over the same period of time. This allows you to get a sort of time averaged value of the mass loading factor. And you know, here this is just showing that value of eta as a function of halo mass in these fire simulations. You guys are killing me with the chat. This is very hard not to laugh. Okay, so again, I'm going to point out, I don't think this is what observations are typically measuring, right? Observations are typically trying to get a measure of the current star formation rate, and then they have some measurement of the current outflow rate. So worth talking about how to connect these two things. I think in his keynote, Dylan just put X and said, this isn't what we're comparing, and we moved on. Okay, so moving in a little bit in scale, an example from my work from the Seagulls simulations, same idea. We can measure the outflow rate in radial bins. Here we're integrating over cells instead of over SPH particles. But you know, it's the exact same idea. I take some bin, I measure all of the mass that's outflowing in that bin. To answer Mark's question, it doesn't have to be only VR greater than 0. That's a choice you can make. But you know, if you don't make that choice, then you could find that at some radii maybe it is net inflow. And you know, you get the same kind of results. Here I'm showing a plot, just plotting these mass outflow rates as a function of radius. You can see I've broken this up into different phases. And again, once you've measured the mass outflow rate, converting to a mass loading is basically just, you know, what's the star formation rate. Another thing I want to note, though, is that in a lot of these small-scale simulations, mine included, the star formation rate is not a self-consistently calculated thing, right? We just put in clusters that correspond to some star formation rate that we want to measure. Whereas, you know, in reality, there's some physical processes in the ISM that are setting that star formation rate. And so that's an important thing to be aware of. Most of the simulations are not doing this self-consistently. Of course, that brings me to highlight one of the simulations that is doing this self-consistently. A really nice example from the Tigris simulation suite, which we've seen also in this workshop. So here you're looking at a plane parallel simulation. So a box that represents a patch of a disk, so you can get nice and high resolution. And there you can do the same kind of thing, but you're going to be measuring horizontal averages. So they take the average rho v over some, you know, horizontal slice in this box. So at a given height z, that gives a mass flux through the surface. That's what's being plotted here. And you can see that depending on what height you pick, here's fluxes for 1 kiloparsec, 2 kiloparsec, 3 kiloparsec in this box. You, again, are going to get different values for the mass outflow rate, right? This is similar to the way in the last slide I was showing you get different values for m dot at different radii. If you want to convert that into a mass loading factor, fine. Multiply the mass flux by the area of the surface. That gives you an m dot. That can be used to calculate eta. Here it's plotted as beta, given whatever the star formation rate is in the box, right? And so here we see, right, there are some trends in this simulation. In particular, you know, the hot phase seems like maybe it has a sort of constant value of mass loading factor with height. It's around 0.1, whereas the, you know, the cold and the warm phases here are clearly dropping off with height. So, right, a point to note is that measurements at different heights or radii will generally give you different values for the mass loading factor. Okay, that's important. And in particular, this is often because some of the gas is outflowing at low heights is just not going to make it to larger distances, right? We talked about this. This is what Filippo talked about in his colloquium as well. If you think of the sort of ballistic trajectory or a fountain flow, then if you're measuring it at low heights, you will be capturing gas that's outflowing, that by the time you get to a higher height, that gas is no longer a part of your outflow. So this is not concerning. It's just something to be aware of. But something else to note is if we go to larger scales, right, gas that's outside of the disk can also get swept up in outflows, which will change the mass loading factor. And I think this is actually a major difference between the values of mass loading factor that are typically measured in these small scale simulations versus in the cosmological simulations, right? If you're looking at you know, a quarter of the virial radius, not all of that outflowing gas was in the galaxy. So we don't need to push as much gas out of galaxies as, you know, as is seen in the mass loading factors measured in these cosmological simulations, right? So to put a picture on it, right? This is where Tigris is measuring mass loading factors. This is where Seagulls is measuring mass loading factors. These are both very small scales compared to, you know, where one would typically measure a mass loading factor in a cosmological or Zoom simulation. Okay, this slide is because Jess asked this question. You know, do the simulations agree on these sorts of things? And there's lots to say about this. Maybe we can talk about it in the discussion. I'm already running long. On the small scale, I would say actually mostly we do agree. In particular, some statements I think we mostly agree on are that values of the mass loading factor for the hot phase of about 0.1 are pretty common. So coming out of the disk, you know, a little ways away from the disk, we're all getting values of order 0.1. We get higher values when we include cool gas that has low velocities, but that's gas that generally will not escape. And we still aren't, you know, generally getting values of mass loading factors that are above, say, 10. There's a really nice plot. This is from Changu's 2020 paper for the Tigris suite of simulations, just showing values of the mass loading factor as a function of surface density of star formation with different velocity cutoffs. So you can see, right, if you include all outflowing gas, you get this really steep correlation between star formation surface density and mass outflow rate, really high rates at low star formation surface densities. But as you increase that cutoff, right, to gas that will actually escape, say you could pick whatever your circular velocity is for your potential, this correlation kind of goes away. So I would say we're not quite sure how to best interpret this, but it's something that, you know, is probably true. On the halo scale, I don't know. I didn't have time to do the literature review, so maybe they can tell me in the discussion. Okay, can I go on for another like 5 minutes?
Sure.
Okay, I wanna just hit on the observations briefly. Fundamentally, it's the same idea. We want to know what the outflow rate is relative to the star formation rate. There's additional challenges, though, right? Star formation rate is usually what I'll call an instantaneous measurement, right? Yes, you can do integrated star formation, but in these big samples, I think we're generally just looking at, you know, something that gives us a measure of the current star formation. You often don't know the geometry of the measured outflowing gas. This is particularly true at, you know, higher redshifts. And typically in observations, you're measuring a single phase. So it's often very difficult to get at the hot gas. We can only do that for really close galaxies. And even in a single phase, say the warm ionized gas, you usually need to make a number of assumptions just to get at the mass that you're measuring, never mind the mass outflow rate. Right, and so the example that I'll show is absorption lines, because this is where we actually have the best statistical samples. Right, if, you know, these are your absorption lines that you're looking at from a down the barrel observation of the galaxy, the easiest thing to measure is the outflow velocity. Nevertheless, there are choices to be made, right? You could use the maximum velocity of this line, but that's a signal to noise dependent quantity. So often in trying to measure mass outflow rates, you know, observers will use something like the line centroid instead. But worth noting that, right, you see there's very fast moving gas in this phase. Then this is straight from Tim Heckman's review, right? The simplest way to get an m dot and mass outflow rate given this absorption line is to relate it to, you know, these quantities: the solid angle, the column density in hydrogen, the mean mass per hydrogen, the velocity, the outflow velocity, that's the one you just pick based on that line, and R, which is the column density weighted radius of the absorbing material. So Why is this tricky? Well, because we really don't know most of these things most of the time, right? These lines are often optically thick, so we're not sure what N is. The ionization correction might be unknown, so we don't know how to go from silicon 2 to silicon. We're not sure what the metallicity is, so we're not sure how to map silicon column density to hydrogen column density. The radius of the outflow depends on the flow structure. Where is the outflowing gas? You have to pick something. And the solid angle of the outflow is often unknown. There's some opening angle. There might be some covering fraction. Okay, so there's a lot of uncertainties that go into measuring these mass outflow rates. Great, but let's say we've measured m dot. Now we're good. Now we're off to the races. We can measure eta. I've been told that instantaneous star formation rate indicators are 100% accurate, so this is no problem. Obviously, I'm being a little bit facetious. There's going to be a lot of scatter in the observations. Nevertheless, if you make a plot like this is a plot from Tim Heckman's paper looking at warm ionized outflows. Warm, I mean 10 to the 4K. And just plotting star formation rate versus outflow rate, you can see this median line is a mass loading factor of about 2. So that's kind of good. It's the right order of magnitude based on what we are seeing in the small scale simulations. I also want to throw in a disclaimer here that observers are working really hard on this, and there's some really beautiful examples, particularly of individual objects, where a lot of these assumptions can be tested directly. And I want to call out some work by John Chisholm. He's been doing a really nice job of this. Nevertheless, getting robustly measured mass outflow rates for statistical samples, which is what we really need, is still a big challenge. Okay, so finishing up, do simulations and observations agree? As I said, on small scales, I think things look kind of okay. We don't have great ways to measure right now the mass outflow rates in the hot phase, which we think is generally driving the winds. But for the warm ionized phase, maybe things are kind of okay. On large scales, I don't know. Again, I didn't have time to do the literature review. This is a plot from Dillon's 2019 paper where he's plotting mass loading factor in Illustris versus a host of observations, and I don't know. Do these agree? What does this mean? No idea. Again, topic for discussion, perhaps. I was going to talk a little about other loading factors, but I'll skip it in the interest of time. But I just want to note, we can play the exact same game with lots of other variables. So energy loading, momentum loading, metal content, these are all things that we can measure. And with some assumption about how much there should be, given the driving physics of the outflow, you can try to make some physical interpretations of what's going on. And the reason I want to highlight it is because I actually think this might be the way forward. Mass is just one very specific thing, but we can probably start to distinguish more between different physical models, for example, for outflows, if we start looking at things like energy and momentum loading as well. You can imagine the energy loading factor between an AGN-driven outflow and a star formation-driven outflow might look very different, for example. Okay, so summarizing. Mass loading is confusing, thumbs down. Mass loading is useful, thumbs up. I don't know. Mass loading is straightforward to measure in simulations. We're not always comparing the same thing. It's tricky to measure in observations, but it's easier to compare. And maybe we can get some interesting physical constraints if we include these additional mass loading factors. This is really just supposed to be a point to bring up for discussion. So I'll stop. I haven't been able to keep up with the chat, so we can talk about these things.
It's mostly about frusta. So excellent. Thank you. Thank you very much, Evan. That was really enlightening. Very well done. And yeah, I think we can chat briefly. Well, no, I guess we should probably just be consistent and send people who want to discuss this to the breakout room. And also a suggestion for relevant comments that bring up questions and whatnot throughout the tutorials. It may be useful to write those questions in the Slack as opposed to just the Zoom, since the Zoom doesn't get necessarily recorded indefinitely. I'll try and copy over relevant questions, not ones about frusta, to the Slack. But yeah, so We will restart in 10 minutes with Marie Lau, Joe Burchett, and Rongman Bordloy's presentation on VoIP profile fitting in observational data. But until then, if you want to discuss this with Evan and have questions about mass loading and its various different incarnations, I encourage people to join the relevant breakout room right now. Thanks, Evan. That was awesome.
Sure thing.